This is a video lesson for Introduction to Orbital Motion. The essential questions for this lesson are, what are Kepler's three laws? What do they tell us about how objects move around larger bodies under the influence of gravity? Okay, so in this video we're going to talk about Kepler's laws, and we're going to talk about a shortened version of Kepler's laws. And in this slide we're going to talk about Kepler's first law. So Kepler's first law states that the planets or any satellite orbit the central body in an ellipse with the central body at one of the focal points. So we have planets or any satellite, so any smaller object orbiting a larger object orbits the central body in an ellipse with the central body at one of the focal points. So here we have our focal point, so that's the central body, and we have our ellipse here, and we'll get into more detail about the axes of the ellipse, but for now we can see we have our little object, our satellite, orbiting around the central body in the ellipse. So the point closest to the central body is called periapsis. So that's this point right here. And the point furthest from the central body is called apoapsis, and that's right here, point furthest from the central body. So the radius, if we were to draw the radius from this point, we would draw the radius out here to the central body. So that would be our radius. Okay, so Kepler's second law says that satellites move faster when they are closer to the central body, and they move slower when they're further away. This is because of the conservation of energy, where we have total energy is equal to the kinetic plus the gravitational potential energy, which is constant, and the conservation of angular momentum, which we'll learn about more later. So out here at periapsis, the radius from the satellite to the central body is a minimum, and the gravitational potential is a minimum. But the kinetic energy is a maximum, and the velocity, therefore, is a maximum. On the other hand, out here at apoapsis, the radius is a maximum. So if we were to draw the radius out here, it would be this whole distance here. So that's the radius. And the gravitational potential is a maximum, but the kinetic potential energy is a minimum, and therefore the velocity is a minimum. So as we said, the satellites move faster when they're closer to the central body. So here, at the closer to the central body, when the radius is small, the radius is minimum, gravitational potential is minimum, but the velocity and the kinetic energy is maximum. And then out here at apoapsis, when the radius is large, the gravitational potential energy is maximum, and the kinetic energy and velocity are minimum. So here, in the middle of the orbit, the radius is decreasing, and the gravitational potential is decreasing, but the kinetic energy and the velocity are increasing. So we can think about our velocity vector getting longer, whereas out here the velocity vector is short, and here the velocity vector is very long. And at this point, the radius is increasing, so the potential energy is increasing, the kinetic energy is decreasing, and the velocity is decreasing. So the velocity vector is getting shorter. All right, let's look at the third law. So the third law says the larger a satellite's orbit, the longer its orbital period. So in other words, as A increases, T increases. And so A is the semi-major axis. So 2 times A, this distance, is called the major axis. And just half of A, or 1A, from the center of the ellipse out to the focal point is called A, the semi-major axis. So as A increases, this distance from the center of the ellipse out to the focal point, which is where the central body sits in an elliptical orbit, the period T increases. And then we have 2 times B, which is the minor axis. So this distance to here, from this point to this point, is the minor axis. And then just from the center of the ellipse out to this edge here is called the semi-minor axis. So looking at the mathematical relationship between period and the semi-major axis, we have period squared is directly proportional to the semi-major axis cubed. So in other words, period is directly proportional to A to the 3/2 power. And for a circular orbit, which we'll get into in another lesson, T squared is directly proportional to R cubed. So for a circle, we have the radius rather than the semi-major axis. So T squared is proportional to R cubed. All right, let's talk about orbits and energy. So the energy of the 2-mass system is conserved in an orbit. So again, total energy is equal to the kinetic energy plus the gravitational potential energy, and those are constant. So to kind of expand this equation, we have total energy is equal to 1/2 mv squared minus g m1 times m2 over r, and again that's constant. So our gravitational potential energy is negative g times m1 times m2 over r, and that's always negative, which is why we have this negative symbol here, which is why we have the subtraction here in our total energy equation. So as R increases, potential energy increases. And as R decreases, potential energy decreases. So here we can see in the graph, it looks like, so the graph behaves as -1 over x. So we've got this exponential curve here. So you can see as R is getting bigger, potential energy is getting bigger. Okay, so continuing with orbital energy. So according to the conservation of energy, we have E1, that's the total energy before is equal to E2, which is the total energy after. So we have 1/2 m2 times v1 squared. So this is the velocity of the orbit before, is equal to, so minus the gravitational energy, minus 1/2 m2 v2 squared minus the gravitational energy at the new radius. So we have radius 1 and radius 2, and these give us different velocities, but the energy is the same in both situations. So when E is less than 0, so when the energy is below the origin on the potential energy graph, like it is here, we have a closed orbit. So it's either an elliptical or a circular orbit. So in this case, the orbit is going to always follow Kepler's law. So when you want to change an orbit, so in this case, moving a satellite to a higher or a larger orbit requires positive work. So you've got to increase the energy in the system to move the satellite to a larger orbit. So in other words, you've got to increase the velocity of the object, the satellite, to move to a higher orbit. To move the satellite to a lower or smaller orbit, requires negative work. So you've got to remove energy from the system. So delta E is less than 0 here. So you've got to remove energy from the system, which is going to slow you down, which is going to make you have a smaller or lower orbit. Okay, so one more slide looking at orbital energy. So if E is greater than 0, then we have an open orbit. And there's a couple of types of open orbits. So when E is equal to 0, we have a parabolic orbit. And then when E is greater than 0, we have a hyperbolic orbit. So here we're talking about when we have potential energies up above the 0 point of this graph. So we have energies that come up over here. So these are orbits that send objects off, not in an actual orbit, but they send objects off. So if here's our central body, we have orbits that go off in these kind of trajectories. So these are trajectories that go off, that send objects either off into other places of the solar system or off out of the solar system and off into the universe as a whole. So as R increases, gravitational potential increases, but the force of gravity decreases. So as R approaches infinity, the gravitational potential is approaching 0 and the gravitational force approaches 0. But notice that this graph is asymptotic. So the gravitational force never reaches and never actually equals 0, because gravity is always additive. So two objects are always exerting some gravitational force on each other, even if they're really very far away. For these types of orbits, as R increases, the velocity is decreasing. Okay, and lastly, we have escape velocity. So these are orbits that have enough energy to send the satellite or the object that's orbiting off out of orbit. So when E is greater or is equal to 0, the velocity is equal to the escape velocity. Okay, and escape velocity is equal to the square root of 2 times g times m sub 1 over r naught. So if we look at our equation for total energy, we have E is equal to kinetic energy plus gravitational potential. So if we expand this, we have 1/2 m sub 2 times v squared minus g times m1 times m2 over r. So if we solve this equation for v, we can see how we get escape velocity is equal to the square root of g m1 over r. So we set this as escape velocity squared minus g m1 m2, and this we call r naught. So we can tell, so this is equal to 0. So if we move g to one side, so we have 1/2 m2 escape velocity squared equal to g m1 m2 over radius squared. So our second masses cancel. Multiply both sides by 2. So we have v squared is equal to 2 times g m1 over r naught. And we take the root of both sides, and we end up with our v escape velocity is equal to the square root of 2g m1 over r naught. And note here that m2, or the mass of the satellite, does not affect the escape velocity. So it doesn't matter the mass of the other object, the escape velocity is the same based on the mass of the central body. So Earth's escape velocity is the same no matter how much mass you're putting into orbit.